Welcome to this iGETT module on map design for the color vision deficient. In other words, for the colorblind. Color blindness is considered by many to be a misnomer. The American Optometric Association prefers the term color vision deficiency. Although one or two authors believe that if you don't have trichromacy, then you are colorblind. However, many authors believe it's a misnomer because most people can see color. It's very, very rare that people cannot see some color. And where we have our greatest difficulty for those that suffer from this, if you're talking about congenital or inherited color blindness, then it's just those folks have trouble distinguishing between shades of red and green. For the elderly, where you have a yellowing of the lens, then they have trouble distinguishing light blue from purple and yellow from green and yellow-green. For me, this was the handout that started it all. Some years ago, I was having my students identify objects on fall color imagery, and one of my students said, "I can't see the labels that well. What objects are you pointing out?" And so using Color Oracle here, this is probably what that student saw. So he was having real difficulty extracting some of my labels. So it set me on this quest to understand better what I should be doing so all my students can see the questions, can interpret better. Now, there are many causes of color blindness. Inherited color blindness is the one we hear the most about and where there are hard numbers. However, injury and illness like glaucoma or MS or macular degeneration, medications, chemical exposure to like styrene, all these things can cause color blindness. And also, as people age, there's a tanning of the lens, yellowing of the lens, which filters the blue. So that's also a problem, and thank goodness we have some recent research where I can put some numbers to that. Now, if we're dealing with inherited color blindness, the most common is what's called anomalous trichromacy. And here what happens is the color pigment in the cones of the eyes gets shifted. Its sensitivity gets shifted. So the red is not as red. The green is not as green. So this is the most common problem, which accounts for a little over 6% of folks. A more severe problem are those where the photopigment in the cone is not functioning or is absent. And here we're dealing with protons where the red photopigment is missing and deuterans where the green photopigment is missing. So they're not trichromatic, they're dichromatic. And blue is very rare. So in inherited, blue works fine for most people. Now, there are no data on the number of people that suffer from illness or medication or chemical or injury. There's no data out there at all. We do have some data on aging that I'll share with you. Now, this matters because we have an aging population. And in fact, in one American government publication back in about 2001, they estimate that the population of Japan, for example, and of Germany may be 50 years, 52 years of age by 2050. So our population in the developed countries is definitely aging. Now, universal design, the whole concept and principles of universal design is that we would provide accessibility to as many people as possible to avoid discrimination and in some cases to comply with regulations. Gardner, in an excellent thesis from Penn State, points out that if you're a web designer and your client is trying to sell product, if a client cannot see, if a person trying to make a purchase cannot see on the web, they're going to click away. If they can't distinguish pricing or product on your website. So this gives us more access to more clients if we're thinking about this. Also, as a professor, I'm interested in my students being productive and being satisfied, but even if you're talking about web design, by considering this, we're going to increase user satisfaction and productivity. In addition to that, it's just the right thing to do. So this is based on the trichromacy theory, which means that you're combining three colors. Red and green give you yellow, and green and blue at full intensity give you cyan, and red and blue at full intensity give you magenta, and then there's shades in between. All these together would give us white. So let's look at the extremes. Let's look at protanopia, where we are missing the photopigment for red in the cones in the eye. And these folks, protans they're called, cannot distinguish between red and green. However, there is a way to compensate for red in that reds do appear dark. So reds with a great intensity will appear dark. The problem is that lighter shades of red and black are going to look the same. So we have to be careful there. But lightness matters in this case. So on the top you're seeing normal vision, and using the Color Oracle I simulated the possible view from a protan. So you can see that the reds look like yellow shades that darken, and that yellow and green are indistinguishable. So this is a possibility of what a protan may see. Now, to show you lighter shades of red and darker shades of red and shades of gray, white to black, if you look on the left, that's normal vision. If you look on the right, that's what a protan may see. So the darker shades of red are distinguishable from lighter shades of red, but lighter shades of red and black are going to be indistinguishable. It's going to be very hard to distinguish between red and black. Let's look at deuteranopia, where we are missing the photopigments for green. And those folks cannot distinguish between red and green as well. However, there is no compensation for the red. So we can't darken the red or brighten the red to make it look darker. Okay, so that's a problem. Now I also want to mention the lesser severe case, which is deuteranomos. In other words, here where the green is shifted more to the red, so you do have photopigment, but its sensitivity has been shifted. So these folks, there'll be a range in which of what they can actually see. It won't be as severe, and they will have a little bit better discrimination between red and green, but it won't be perfect. And this is actually the most common inherited color blindness issue. So looking at the extremes, at the top, normal vision, normal view, and at the bottom what a deuteran may see, and you can see again that the green and the yellow and the red become very indistinguishable. So big issue there, and blue is pretty close to normal in both cases. The third is tritanopia, and this is very rare. I want to mention it and show it to you because as you'll see in a minute, aging causes a triton-like effect. And those rare cases where the blue cones are not functioning properly, blue and greens are confused and yellow and violets are confused. So this is a Color Oracle simulation of what they possibly might be seeing. Again, the top view is normal view, the bottom view is tritanopia. And again, you can see blues and greens are an issue, so it's a problem. Again, rare, and I'll come back to aging in just a second. So I'd like to discuss briefly the effects of aging, what Schneck and her co-authors call a triton-like effect, which is due to the yellowing of our lenses as we age, which causes a yellow filtering effect. This disrupts the blue-yellow vision. Now, they studied about 960 people between the age of 58 and 102, probably the first study that looked at older populations. And there was clearly evidence of, as you get above 60 and increase in age, there is more and more of an effect, this Triton-like effect. And in populations, now there were two different color blindness tests, that's why you're seeing two different percentages there. But in populations of 80 years and more, it was either 30 or 50% of that population that they studied saw effects of that they did not pass those tests. And of those that did not pass the test, 80% had an issue with distinguishing light blue from purple and yellow from green and yellow-green. So yellow from green and yellow from yellow-green. So it is a Triton-like effect, but it's not exactly the same. But again, green shows up as being a problem and distinguishing green and yellow in every case. So there's a couple of things to keep in mind, as Dr. Brewer from Penn State points out, and Clark also. Color is three-dimensional, and you have to keep that in mind. There's hue, there's value, there's chroma, and you need to keep that in mind, that it's three-dimensional. Also, Dr. Brewer points out that there are perceptual dimensions to color. Okay, for example, I just painted a wall in my kitchen, and it's supposed to be a green, but next to another wall it actually looks blue. So the color pairs make a difference. What it's combined with makes a difference. Keep in mind that for inherited, red and green, distinguishing between red and green is the most common problem. For the elderly, the yellow-green is going to be a problem. So the point I'm trying to make, and we'll repeat later, is that green appears over and over again to be an issue. Except for the elderly, blue for the inherited population is recognizable by most people. Now, what are the recommendations? Multiple authors recommend that you watch the color pairs that you select. Make sure that that color combination is unambiguous. Avoid using class differentiation and color by itself. Use another visual variable if you are doing class differentiation. Annotate the features, okay, so that there's no question. And it would be best if you can reduce the number of classes. The fewer number of classes that you can use to illustrate your data or ranking, then the easier it will be to get a number of colors. So if you have 3 classes, that's going to be easier than 4 classes, which will be easier than 5 classes above that. You're going to find it challenging to find colors that everybody will be able to see. Brewer and Clark point out that these are the colors of concern. So the hues red, orange, brown, yellow, beige, green are confusing. And magenta, gray, and cyan may be indistinguishable for some. Now, mostly what they focused on were the inherited population. But it's important in that inherited population that you avoid red and black combinations, because in lighter shades they will not be able to distinguish between red and black. And again, this only matters where there's meaning attached to the color, right? And we can use lightness to differentiate. If we can find a hue that works, we can use lightness steps to differentiate that range of importance. I'm going to go through this pretty quickly. I'm not going to mention all these, but just so you know, in either of these publications, you can see this list of color pairs which are recommended, which should work for most populations. Now, Jenny and Kelso directly addressed map making. And so to repeat a little bit, if we're dealing with point and line features, saturation they found really did not help. It was only a slight improvement. It does not help very much if you're talking about red and green impaired populations. However, what they found is shift away from green to blue. By eliminating that green and shifting to the blue, that is really will avoid a lot of confusion. And again, the best solution is to annotate and use the visual variables in combination with color to make your point. And everybody will be able to distinguish your classes and rankings much better. Now, what if we're dealing with raster cells or areas? We can vary the lightness using a red, orange, yellow end of the spectrum. We can omit the yellow-green to avoid the green confusion. Okay, avoiding green altogether should work for most of the population. So their recommendations are use a red, orange, yellow, light blue, dark blue. Okay, and so what Jenny and Kelso are also recommending is if you can align your data so that the pivot point of the data is at the yellow-blue transition, that will work really well. So a red, orange, yellow, light blue, dark blue range. Now I recommend you look at the illustrations in Jenny and Kelso. That article is available online and it's in my references, so check that out because they have some really good illustrations. So looking at this all together, what I've done is I tried to use just a red, orange, yellow, light blue, dark blue range here, and you can see the effects on those different populations. A couple of final things. One of the things you really should investigate are Cynthia Brewer at Penn State, her Color Brewer. Color Brewer 2. If you do a Google search for it, that tool will come up and it will give you colors that will work for the colorblind. It's geared towards inherited color blindness. She points out that again that the tools that we have in, let's say you're using ArcGIS, the tools that we have are not perceptually scaled, and she recommends that you do it by eye. Don't use RGB values of 100, 100, 100, and then shift and do RGB values of 150, 150, 150. That may not work. You really need to do that by eye. But the Color Brewer will give you colors and will give you those RGB and other values that you can insert in here. So it's a very, very useful tool. So check out the Color Brewer 2 and just do a Google search. So one of the things that she's based her color recommendations on is the colorblind confusion zones. She has an excellent illustration in this. I don't have copyright permission, but if you go to her website, you can, or the book, you'll see the colorblind confusion zone illustration, and she recommends that you jump zones. So that if you skip a zone and you're one zone apart, then those colors should work. So anyway, check out that illustration, check out her website or her book. Again, here's the website. The book is referenced in the references at the back. And then before we leave this topic, I want to mention a bunch of really excellent tools. The Color Brewer 2 at colorbrewer2.org. VizCheck.com is worth checking out. And I use the Color Oracle, which is also an excellent tool, and then you have a couple other resources here. So please check these out. You'll find you can download VizCheck, you can download Color Oracle. Color Brewer 2 has some tools that you can bring into ARC. So these are very, very useful tools. So I will stop speaking at this point, and what follows is a set of questions followed by their answers, and then followed by a list of resources. The last slide gives a URL link back to our web page. So at this point, I want to thank you for listening to this module on map design for the Color Vision Deficient. I hope you found it useful. Thank you.